Okay, so in the previous hour I talked about two different ways of classifying systems, and I think it's easier to remember the definitions. Okay, so it's easier to remember what makes a system static or dynamic, or what makes a system time varying or time invariant. So that's why I told you that. But also, you can also recognize systems by looking at their equations, because as engineers, we'll be dealing more with equations. Okay, so in your future life, you will be always dealing with equations for different purposes. So you should also be very well equipped with how to handle those equations. So that's why mathematics courses are really very important. So the calculus courses and the differential equations and any other mathematics course you can take will help you a lot. So anyways, so let's well, I already told you that for static systems the equations are non-differential equations, whereas for dynamic systems the system equation is in the form of a differential equation. Okay, so if you see a system equation and it contains derivative terms or integral terms, so integral terms are also, as you know, a part of differential equations. So you can immediately say that you have a dynamic system. Similarly, for time-varying systems, you can see that when you look at the equation. So let me go back to this file. Okay, so if you have system equations, I don't know if you can see that, but if you have time t depending explicitly in your equation, that means your system is time varying. So if you consider, for example, the missile example, in that case the mass of the missile is changing as a function of time. So you can write, so the mass is not a constant number, but rather it's something changing with time. So you can use this function, for example. So if t is equal to 0, you have a certain m0 value, but if as t increases, this m0 value drops down. So this t term in your equation means that you have a time varying system. Okay, so if you come back here, so this was the previous example, remember? Output is equal to 2 times the input. So this is a time invariant system because you don't see t explicitly in that equation. But if you had something like t times u, then this is obviously a time varying system because of this t term. Okay, so it's very easy to recognize time varying systems from their equations as well. Okay, now let's come to this third classification. Okay, so this time we again divide the entire set of systems into two. This time we use the property of linearity. This is a very, very important property of systems. And so if you have a system that is either a linear system or a nonlinear system, so at times it may be quite tricky. So you may have trouble deciding whether you have a linear system or a nonlinear system. But if you consider the definition, as always, I think it will be very easy to see that. So let me copy the definition from here. So linear systems have one very important property, which is the superposition principle. A system is said to be linear if the superposition principle holds. If not, that means you have nonlinear system. And you must have heard about the superposition principle. So that basically says that, suppose that you have a system, you give an input U1, an input signal, and that gives an output Y1. Another input U2 gives the output Y2. So if this system is linear, then any linear combination of these two inputs will result to an output that is the same linear combination of the individual outputs. That means if you apply this as the input, you take the first input, multiply that with some number A, some real number. You take the second input, multiply that with some another random number B. So this is your new input. If the output is equal to this, which is A times Y1 plus B times Y2, then this is a linear system. This is the superposition principle. Okay, so again, let's think about some examples and see if you have if the systems that we consider are linear systems or nonlinear systems. Okay, so let's start with an aircraft. And for input we have the elevator, and for output let's consider the pitch angle theta. Okay. So we give it an input. So this is our first input, and we get an output like this one, for example. So this is the first output, theta 1, and the so let's say this was 5 degrees. So for the superposition principle to hold, we should be able to multiply this input with some random number, arbitrary number, and the output should be multiplied by the same number. But in the case of an aircraft, for example, if you choose A to be 10, then you will see that the superposition principle does not hold, and it can't really hold, because for this to be true, you need to multiply the input with this number, which requires you to give an elevator input of 50 degrees. But obviously that's not possible, because the elevator has a certain range, and we cannot really deflect an elevator more than a certain angle. So obviously, due to that, an aircraft is a nonlinear system. Okay, because you have an elevator, and so this deflection is limited to a certain range. It's 25 or 30 degrees at most. So this is a reason why an aircraft is obviously a nonlinear system. Or another, well, actually I think this was written here. Actually the same thing was written here already. So we cannot even apply a 100-degree elevator deflection. So that's because of the input is limited. So that's the reason why we said that the aircraft is nonlinear, because the input we apply is limited. It cannot go over a certain range. But there are other reasons why aircraft is nonlinear, and that's actually explained here. So let me just copy everything. Okay, so for deflections that are within the operating range of your elevator, if you give too much control input, the behavior of the aircraft will change. That's because the aerodynamic properties change, right? So, for example, if you give, let's say, 20 degrees of elevator deflection, which is within the operating range, for example, your angle of attack may increase a lot. So your angle of attack may increase so that your aircraft can stall. And in that case, obviously, the lift force, drag force, moment, everything will be changing. That means your aircraft will give a different output. So let's say in the first case, you T, and this is the elevator. So you give a certain elevator input. So let's say this was 10 degrees. And as the output this time, let's consider the angle of attack, or let's consider the speed. So your aircraft was initially flying at some steady state speed, and due to this elevator deflection, the speed will start changing. So the aircraft will be slowing down, let's say. In the second case, you give a much larger elevator input. This is 20 degrees. But this time the aircraft will stall, right? So that means the response will not be twice of this response, but instead it will be, so since the aircraft will stall, it will, the speed will be reducing down. And the response is not twice the response of the other one. So that also means that you have a nonlinear system. Okay, so as I said, linearity property is a very important property. That's because a lot of the theory for control systems are valid for linear systems. But on the other hand, in practice, in real world, every system is somehow nonlinear. So if you consider any system you can think of, it will always you will always find things that make it nonlinear. Because it's in the nature. In fact, nature is nonlinear. So even in the cars, there are obvious nonlinear systems, because the same thing applies for cars. So in this example, we said let's give 50% gas pedal input and we get a certain acceleration. If you step on the gas twice as much, the speed of the car will not be changing 2 times the previous change, right? And again, the input is limited, so you cannot go over 100%. So you cannot multiply this with any number that is greater than 2. So that means the superposition principle does not really hold. Is nonlinear to a certain extent, let me say. Well, simply because of this reason, every system is going to be nonlinear, because since you cannot apply infinite input to any real system, the superposition principle fails due to this scaling constant cannot be too large. This constant in definition, so you cannot make this a very large number. So that's obviously why every system becomes nonlinear. But in most cases, there are other reasons for a system to be nonlinear as well. For example, in the case of aircraft stalling is obviously a reason what makes an aircraft nonlinear. Okay, so just like the previous properties, you can distinguish or recognize a nonlinear system from its equation. And it's written here. The mathematical models for linear systems contain system variables and their time derivatives alone. So we said the system equations for dynamic systems are differential equations, and those differential equations are the independent variable is time. So you have derivative terms with respect to time, and since you have so remember I told you that these are signals of time. So the system equation will look something like this: the nth derivative or some I don't know, smaller derivatives, so the input variable is u, the output variable is y, and for a linear system, these variables and their time derivatives appear through linear functions. So if all these coefficients are constant numbers, then this is an equation for a linear system. If you have something like in the system equation, this is a nonlinear system because you have output and input appearing as a multiplicative term. Okay, so this cannot be, there cannot be multiplications of such terms, or you cannot have higher order terms. So this is a nonlinear system. Or if you have something like u squared, this is also nonlinear because you have this time the input signal u multiplied by itself. So that's another high order term. So this is also a nonlinearity. Or something like du over dt times u. This is also nonlinear because this time you have the multiplication of these two terms. Okay, so also if you have nonlinear functions such as the sine function, for example, sine of u, the sine function is also a nonlinear function, right? If you consider the superposition principle, it doesn't satisfy that principle. Okay. So does everybody see why the sine function is a nonlinear function? It doesn't apply to superposition, right? So if you have so this is square root of 2 over 2, right? Sine pi over 4. So if you multiply the input by 2, the output is not equal to this, right? So it's something else. The superposition principle fails there. So the sine function is a nonlinear function. Or the absolute value. That's also a nonlinear function, right? So if you have a system equation, which is dy over dt is equal to the absolute value of u, this is also a nonlinear system because you have the absolute value function, which is a nonlinear function. Again, if you just consider superposition principle, then you will see that this doesn't satisfy that principle, so it is a nonlinear function, and hence a system with such an equation is a nonlinear system. Okay, so if you consider these three classifications of systems, each classification divides the system into two, but then you can combine these two, all these classifications, and that means you will have So if you consider all these classifications at the same time, then you will be able to say things like, if your system falls somewhere here, so that means your system will be static and linear and time invariant. Or if it falls somewhere here, then your system will be time varying and dynamic and nonlinear. Okay? And you can again see where your system falls on this diagram by considering the definitions, and you can also see that by just looking at the equation for that system. So let's consider some examples. Let's say you have a system for which the equation is sine of u. So this is a static system, right? Because there are no derivative terms. It is a nonlinear system because there is this sine function. It is also a time invariant system because there is no t term appearing explicitly. If you have if you, for example, have derivative of u here, du over dt, then this now has become a dynamic system, right? So this should be dynamic, still nonlinear and still time invariant. Well, I guess you get the idea, right? You can generate a lot of examples, but so I think this is a really important concept, because I see experienced engineers like the graduates of this department who have taken all these controls courses, and they get difficulty in deciding whether the system they have at hand is linear or nonlinear. But in fact, it's a very, very simple check, and it is you can, in fact, if you remember these definitions, you can easily see whether your system, you can categorize your system. Okay? Okay, so let me give you just two more examples. I feel something like dy over dt is equal to so you have input and output, you have derivative terms, so this is dynamic. So the input and outputs and their derivatives are appearing as linear functions, so that is a linear system. But you have this coefficient, which is a function of time, so that makes that a time varying system. So if all the coefficients in the above equation, which are A, B, and all the others, are constant numbers, then the above system is a linear system, dynamic and time invariant. Okay, so a lot of the control systems theory is developed for such systems, linear, dynamic, and time invariant systems. So if you have a nonlinear system, then the theory, the mathematical theorems we have are not applicable anymore. Or if you have a time varying system, similarly, a lot of the theory we will be using is not applicable anymore. So what we do for such systems is we consider those systems in a limited range, in a limited domain. And by doing that, we can approximate that system as a linear, dynamic, and time invariant system. So for example, if you consider the aircraft example, so obviously if you start giving too much control inputs, your system will start behaving like a nonlinear system. But if you limit your elevator deflection to small values, then your system will be behaving similar to a linear system. For example, if you say that your elevator deflection angle should be less than, let's say, 5 degrees, then within that range, the superposition principle will be applicable. So if you choose these coefficients, A and B coefficients, such that the overall input never exceeds 5 degrees, then your system will be very similar to a linear system. Similarly, you can use that for other nonlinear functions as well. For example, if you consider the sine function, so the sine function looks something like that, right? But if you consider theta values, let's say 0.1 radians, then within this range, the sine theta function can be approximated by the theta itself, if theta is less than a certain value, right? So that's what we do in practice. So we consider the motion of the system to a certain range, and then the linear system theory will be applicable for that case. Okay? And there's one other classification I would like to talk about, and that is actually explained here. So let me just copy here first. So this is lump parameter versus distributed parameter systems. In most systems, or I shouldn't say most, in some systems, there is only one independent variable, which is time. But in other systems, there are additional independent variables such as space, for example. Okay, so let's consider this problem. You have a rod here. I don't know if you can see that, but let me just draw it again. So you have a rod here, and you heat it with a heating source here. Suppose that you light a fire here, and this heat source heats up this bar. So in this problem, there are two independent variables. The one is time. So you can consider. Okay, so let me just draw my system here. Temperature of the bar is our output, and the input is the heat applied. Okay, so the input heat applied is a function of time, but the output, so let me use capital T here, is a function of T, but also it's a function of space as well, right? X. If you consider X to be this direction, and if you consider this to be an infinitesimally thin bar, so this is dy. So there are two independent variables here, right? T and X. So that means as you apply input to the system, you can study the output as a function of time. So that means as you apply more heat, the temperature will be changing. But also you should consider the variation with respect to x as well, because the temperature here will be different than the temperature here, right? Because the heat is applied at this point only, but it's so these systems have more than one independent variable. So for such systems, in the equations you have to consider the differential derivative terms with respect to every one of those independent variables. So in the case where there's one independent variable, you only have derivative terms with respect to t, right? dy over dt, or you have higher order derivative terms. So if there's one independent variable, but if you have two independent variables, then this time you need to talk about partial derivatives. So you take derivative with respect to time, also you take derivative with respect to x. So you have partial derivative equations. So mathematically speaking, this is, you can intuitively see that this is a harder problem, right? Because in the one case you have a differential equation where you have derivative terms with respect to one variable only. So these are ordinary differential equations, if you remember. But in this case, you have to deal with partial differential equations. So if you have a system like this where you have many independent variables, then you can approximate that system using the lumped parameter model. So what you do is, so let me go back here. So before I start talking about that, let me just come back here. Okay, so I can talk about more about this, but I don't think it will be any useful, since in this course we will not really consider that. But so it's just sufficient that for you to know that in mathematically speaking, systems with many independent variables are definitely much more difficult to deal with. And hopefully you appreciate that from your math courses. If you have an ordinary differential equation, then you can solve that under certain assumptions. But if you have a partial differential equation, then those equations are much more difficult to solve. So you have much more restrictive assumptions under which you can solve such systems. But for ordinary differential equations, it's much more easier to deal with. And in control systems, we only study systems with one independent variable, which is time. But if you have a distributed parameter system where you have additional independent variables, then those systems can be simplified by using the lumped parameter model, and I will be talking about that tomorrow. Okay? Do you have any questions? Okay, so we have tomorrow. Tomorrow I will talk about these distributed parameter systems a little bit more, and so I will see you tomorrow.